Welcome and thanks for being here. I'm Alfredo Perez. I'm a Senior Technical Marketing Manager with the Bluetooth Special Interest Group. In this session, I'm going to be speaking about two features that are being introduced by the SIG to enable and standardize wireless human interface device solutions using Bluetooth technology. So for anyone in the audience new to human interface devices, let me just provide some context in this slide and the next one. HID has gradually evolved over the last 30 years, approximately. It began in the mid-1990s with the USB HID specification, which standardized the way I/O devices communicated with computers over a wired USB interface. Then, in the early 2000s, the Bluetooth HID profile adapted USB HID to operate over a Bluetooth Classic wireless link. Then, in the early 2010s, the Bluetooth HID over GATT profile was adapted, but this time to operate over a Bluetooth Low Energy wireless link. Now, in the mid-2020s, the Bluetooth HID over GATT profile is being enhanced with new features that enable higher report rates to enable better responsiveness in HID applications. And within the Bluetooth SIG, these enhancements to the HID over GATT profile are what is known as the ULL HID project, where ULL stands for ultra-low latency. In the near future, that project name will be replaced by an official customer-friendly name that's more intuitive and more meaningful for users. So just FYI. Now, why ultra-low latency? Who needs this? So there are emerging and traditional wireless HID applications that require higher report or polling rates from what the Bluetooth HID over GATT profile has supported to minimize latency, to improve responsiveness, and to deliver better experiences for HID users. In the gaming market, for example, most first-person shooter or rhythm games run with 1 millisecond granularity for a HID decision. Hence, the latency of the controller greatly impacts the outcome of such games, especially in multiplayer settings. In the extended reality market, advanced XR systems require single-digit millisecond I/O latency for near real-time responsiveness. For XR, then, the latency of the I/O device translates to over or undershooting movements for the user that directly impact the virtual interaction with objects in a virtual environment. In the productivity market or productivity device market, I/O devices are starting to require higher report rates to catch up with the increasing refresh rates being supported in advanced displays. Also, if you have lower latency mice or styluses, those give better visual approximations of circles or curved shapes on a screen, which is important for HID users that work in the design or the arts, etc. So with that context in mind, now let's come back to the Bluetooth ULL HID project. In a nutshell, Bluetooth ULL HID adds two new features to the HID over GATT profile specification that are named HID ISO and HID SCI. HID ISO uses LE isochronous channels, while HID SCI uses shorter connection intervals to implement the mechanisms that enable the ultra-low latency performance. Both HID ISO and SCI are Bluetooth core specification capabilities that I will elaborate on upcoming slides shortly. The key thing to keep in mind is that HID ISO and HID SCI can achieve a maximum report rate of 1 kilohertz or higher to allow targeting HID latencies of 1 millisecond or lower. This is important because it represents an improvement factor of about 7.5 or more versus the default max report rate achievable with HID over GATT profile. Now, these two features offer HID designers and developers flexibility to implement ultra-low latency HID solutions, as now developers can choose the option that's best suited for their architectural needs and constraints. Overall, the ULL HID project strengthens Bluetooth as the leading technology for mainstream wireless HID And the slides that follow will be taking us through a high-level technical overview of both features. Before jumping into the technical overview, very quickly, let's review one more thing. A Bluetooth profile is a specification that defines rules and requirements to standardize the way Bluetooth devices communicate for a particular use case. Profiles ensure interoperability between products or solutions from different manufacturers or vendors. So in the case of the HID over GATT profile, HOGP enables low-power wireless communication between HID devices and HID hosts using Bluetooth Low Energy. The GATT part in the profile name alludes to the use of the GATT protocol in Bluetooth LE to organize data in a hierarchical structure based on services and characteristics, to exchange data following a client-server communication model, and to encapsulate HID input and HID output reports. The role, service, relationships, transport dependencies, etc., required for human interface device operation and standardization are defined in the HID over GATT profile. Now, the HID ISO feature that I'm talking about is introduced in version 1.1 of the HID over GATT profile. And among other things, HID ISO introduces a new service called the HID ISO service. It defines requirements for a HID host and a HID device to support HID ISO, and specifies feature components like the hybrid operation mode, which I'll describe in another slide, a new packet structure, a new protocol to manage acknowledgements and retransmissions for reliability, etc. Now, speaking of HID SCI, HID SCI is going to be introduced in version 1.2 of the HID over GATT profile. HID SCI introduces updates to the HID service that already exists and it's used with the HID over GATT profile via new and modified characteristics. And it also defines requirements for a HID host and a HID device to support HID SCI. And I'll be talking about all of this in the upcoming slides. So now let's proceed to the technical overview and start with HID ISO. HID ISO is a feature that allows sending input and output HID reports over LE isochronous channels via connected isochronous streams. The key highlight about HID ISO is that it reduces the minimum HID report interval from 7.5 milliseconds down to 1 millisecond. Inversely, this means that HID ISO allows increasing the max report rate supported by the HID over GATT profile from 133 Hertz up to 1 kilohertz. With HID ISO, the report interval is set by the HID host, which selects the lowest or best interval that can be supported by both the HID host and the HID device. The HID ISO feature itself is enabled through an operation mode defined in the HID over GATT profile called hybrid mode that allows exchanging the HID reports using isochronous channels and also the GATT protocol. The thing to keep in mind is HID ISO has already been formally adopted and introduced in the HID over GATT profile release version 1.1, which was adopted in August of 2025. So this feature is already out, publicly known, and adopted. Now, in the context of HID ISO, there are important things to understand about LE isochronous channels. The first thing is ISO channels were introduced with Bluetooth Core 5.2 to enable LE audio. Isochronous channels allow communicating with time-bound data to one or more devices for time-synchronized processing, either in connected or connectionless fashion. They define also connected isochronous streams, which is a connection-oriented logical transport that supports bidirectional point-to-point communication based on the use of ISO channels, of course. In connected isochronous streams, all the transmit and receive activity occurs in scheduled time slots that are called sys events and sub-events. The events occur at a regular interval called the ISO interval, and then the events subdivide into one or more sub-events. The sub-events are the actual slots that are used to exchange ISO protocol data units, or PDUs, and each sub-event takes place over a different radio channel to minimize interference. A key advantage of connected isochronous streams is that they can support variable flushing periods for payloads, variable size data contents and packets, and a variable number of sub-events. And all of this allows isochronous channels to support a broad range of data rates, latencies, and retransmissions, which are critical for HID ISO. Now, the diagram that is going to come up on this slide will help illustrate the relation between connected isochronous streams, events, sub-events, and other parameters to be aware of. So to begin, a connected isochronous streams must be formed through an asynchronous connection. That means that when two devices first connect, the connection is established via ACL, logical transport. Then after that, the devices can set up the isochronous connection via CIS. Now, the connected isochronous stream will carry the ISO data, and the ACL connection will carry link layer messages to set up and control the connected isochronous stream. The ACL link will be providing timing reference for the scheduling of sys events, but if the ACL connection is lost, all the connected isochronous streams associated get terminated. Now, connected isochronous stream events, which I'm going to show here, start at a moment in time that's called the sys anchor point. Those anchor points are regularly spaced, which means all sys events have a constant time interval that's equal to the ISO interval. Sys events end either with the last scheduled sub-event or earlier events through specific bits that are transmitted by the central or peripheral device. But anyway, a sys event, like I had mentioned, can be subdivided into sub-events. You can have up to 31, and the sub-events are spaced out by what's called the sub-interval. Now, with all that, the first sub-event starts at the sys anchor point, and successive sub-events are spaced apart by the sub-interval. So this is the activity that starts happening in the different sub-events, and that's how you start moving information with the connected isochronous streams. The tables here at the bottom include or mention some parameters that are needed for the configuration of a connected isochronous stream, such as the number of sub-events, the burst number, the flush timeout, and number of retransmissions allowed. We're not going to go over all of these in detail, but just be aware that all this is needed for the configuration of ISO channels. Now, I mentioned that HID ISO introduces a new HID ISO service. This service defines two new characteristics. The HID ISO properties characteristic, which describes all the ISO-related properties supported by a device, and the LE HID operation mode characteristic, which configures HID ISO behavior and operation mode changes. In this slide, I show the structure of each of the characteristics depicted with the blue boxes. Each box represents a field in the characteristic. I'm showing the size of the field in octates and some description there that for the sake of time we're not going to discuss here today. Now, in terms of requirements to support HID ISO now, a host must be able to discover the HID ISO service through primary service discovery, as well as the HID ISO properties and LE HID operation mode characteristics that I just mentioned. In addition, the HID host must support the hybrid and default operation modes that are defined in HOGP version 1.1 and the switching between these. Also, it must be supporting the configuration of isochronous channels, obviously, to enable hybrid mode, a new HID ISO packet structure, a new HID ISO protocol that's introduced with the profile, and a sequence number management for reports that are transferred over those isochronous channels. In terms of the HID device must be able to do basically all that. Just one thing to note is that when it comes to switching operation modes between hybrid and default, the HID device can make a request for a switch, but only the HID host can actually initiate it. So at a high level, the way to enable HID ISO is through this new operation mode called hybrid mode. Hybrid mode allows exchanging HID traffic over both isochronous channels and GAT. You would use isochronous channels for the low latency traffic and GAT for latency and sensitive traffic. With the introduction of this new hybrid mode, the legacy mode for HID traffic exchange over GAT is now referred to as the default mode in this profile. And default mode is there for use cases where the typical report rates achievable with HID over GAT are adequate, and for interoperation with the HID over GAT profile version 1.0. Now, to switch to hybrid mode at a high level, the host must write to the LE HID operation mode characteristic an opcode that's needed to select the hybrid mode. And then once isochronous streams are established, the host and the device can then transition to the hybrid mode. If you want to switch back to default, then once again, the HID host must write to the LE HID operation mode characteristic an opcode to select the default mode. And the host will terminate the ISO stream, and the device will revert to default mode automatically. To wrap up this HID ISO technical overview, this slide will illustrate an example of a reasonable scenario where a 1 kilohertz report rate can be achieved using the 2 megabits LE5. If we define a connected isochronous stream with an X number of events, 5 sub-events per sys event, an ISO interval of 5 milliseconds, sub-intervals of 1 millisecond, a burst number of 5, etc., we would end up with something that on a timing diagram would look like this. If the communication between central and peripheral device consists of null packets, and between peripheral and central you're sending gaming data, you can calculate the null and gaming data packet sizes and timing based on the calculations I have there on the screen, and you will get to the calculation that once you account for interframe spacing and other things, you would require about 500 microseconds for HID ISO activity. So this means that you will have another 500 microseconds left in the 1 millisecond subinterval to bring in ACL-based activity. So depending on the packet sizes being exchanged through ACL, you can potentially fit into the same timing window for a sys sub-event, isochronous data, and ACL-related data, which would allow the HID ISO protocol to operate at a max rate uninterruptedly. So now let's move to the technical overview of HID SCI, which is going to mirror the flow and detail level used in the slides for HID ISO. HID SCI is an upcoming feature that allows sending input and output HID reports over GATs, but this time controlling the link using shorter connection intervals. The key highlight here is HID SCI reduces the minimum HID report interval from 7.5 milliseconds down to 1 or less under certain conditions, because by definition, shorter connection intervals can support or bring down the connection interval down to 375 microseconds. Inversely, this means that HID SCI allows increasing the report rate for HID over GAT profile from 133 hertz to 1 kilohertz or higher. With HID SCI, again, the report interval is set by the host, which selects the lowest or best connection rate based on the SCI supported capabilities by the host and the device. And the HID SCI feature is going to be introduced with version 1.2 of the HID over GAT profile. And this is targeted for public adoption and release in late Q2 of this year. So it's coming up. In the context of HID SCI, these are the important things to understand about shorter connection intervals. SCI was introduced with Bluetooth Core 6.2 late in 2025. SCI allows configuring links using the ACL transport with connection intervals shorter than 7.5 milliseconds, which used to be the previous limit for Bluetooth LE. SCI reuses existing LEAC links for data and for control. But the important thing is SCI sets a new framework for negotiating and applying timing parameters based on 3 value ranges that are shown in this table, which use different timing resolutions and support different minimum connection intervals, with the extended value range covering anything between 375 microseconds up to 1.25 milliseconds. The key benefits of SCI are that it can be used with any Bluetooth LE5, and that it works with a new feature that was also introduced with Bluetooth Core 6.2 called the ACL flush timeout, which wasn't available before for ACL links. This slide, I'm not going to spend much time. It's just to illustrate if you use shorter connection intervals to enable ultra-low latency, you will rely on SCI to bring down the connection rate down to a value that's supported in the value ranges mentioned. But then the thing to keep in mind is that once you're able to bring down the connection rate to sub-millisecond if you want, you can play with additional parameters available to configure an ACL connection to support different use cases and play with power optimizations or data delivery optimizations using the subrate factor, base event, peripheral latency, etc. I'm not going to go into the details, but just be aware of that. Like mentioned, HID SCI introduces new characteristics that are added to the HID service. These are the HID SCI information characteristic, which allows discovering the minimum supported connection interval by a HID device, and the HID SCI mode characteristic, which allows to determine the HID SCI mode currently being used by the HID device, as well as to notify the HID host of any HID SCI mode changes. Similar to the HID ISO slides, the structure of the characteristics is depicted. I'm not going to spend much time here. For completeness here, there were also updated characteristics to the HID service. They were the HID information characteristic, which holds the set of values for HID device attributes, and the HID control point, which defines mechanisms and commands for HID device control. To support HID SCI, these were the requirements that are being introduced to HID Orgat Profile version 1.2. The host device, HID host, must be able to support shorter connection intervals. It also must be able to discover the HID service through primary service discover. And note the version 1.1 of the HID service. That is the updated service that includes the support for HID SCI. Then the host must also be able to discover the characteristics already mentioned: HID information, HID SCI information, HID SCI mode, and HID control point. And optionally, it must be able to also configure flush timeouts and to change characteristic values using the add-write procedure. On the HID device side, same thing. The device must be able to support shorter connection intervals, HID service 1.1. It must be able to expose its HID SCI capabilities, attributes, and modes through the different characteristics. And it must be able to provide optional configuration options for flush timeouts on the input report side. Note that in comparison with HID ISO, HID SCI doesn't work with isochronous channels, doesn't require a new packet structure, new protocol, or new sequence number management at the application layer level, like HID ISO does. And HID SCI doesn't require HID ISO operation or support. It just runs on its own. Last thing here is at a high level, just to enable HID SCI. HID SCI has nothing to do with hybrid mode. in the case of HID SCI, HID SCI simply leverages optional modes that are being introduced to adapt transport parameters for the ACL link. And all traffic for the HID application are going to be exchanged over GATT. To switch to HID SCI, a HID host must write the HID control point characteristic and configure the HID device to the desired HID SCI mode. So when you go and review the HID over GATT profile document, you will see there's several HID SCI modes outlined, and their names are fast, default, full range, low power, and none. I'm not going to cover those here, but just be aware. And to switch between HID SCI modes, like the ones that I just mentioned, both the HID host and the HID device can renegotiate or update their transport parameters. The device must initiate the connection update request with the HID host, and then the HID host must write again the HID control point characteristic to initiate the negotiation of new parameters. This diagram illustrates very briefly how the switching from default to HID SCI modes happens. Again, the initial connection is going to be based on ACL, regular legacy connection, and then you'll go through the process where the host will be discovering the HID service and the characteristics needed to decide which parameters to use for a HID SCI configuration. Very straightforward. So now that concludes the overview of the HID SCI feature. Let's summarize things. What did all of that mean at the end? So we had HID over GATT profile version 1.0, and late last year we introduced HID over GATT profile version 1.1. 1.1 introduced the HID ISO feature. It was adopted in August. Support for HID ISO is optional. So if you're going to be enabling ultra-low latency, that specific feature is not mandatory, it's optional. The transports used are both LEACL and LEISO, ISO for the higher report rates. The max report rate that can be achieved is up to 1 kilohertz. The report interval remains constant because the connected isochronous stream stays programmed consistently to the rate chosen when the stream gets configured. In terms of data reliability, the HID ISO protocol is introduced to handle retransmissions. Data flushing is by default enabled with isochronous channels. The data delivery mechanism is deterministic because of isochronous channels. If we look now at HID over GATT profile version 1.1, here is where we introduce the HID SCI feature. This is coming in Q2 of this year. HID SCI as well is an optional feature, not mandatory. The transport used in this case is all based on ACL, but ACL with shorter connection intervals to achieve the higher report rates. The max report rate achievable with HID SCI is 1 kilohertz or greater, depending on implementation and resources available. We would say that the report interval is adaptive because on the fly you could be changing the report rate based on application needs. Retransmissions are handled at the link layer level for data reliability. Flushing, which wasn't supported before in the ACL transport, now are enabled through the ACL flush timeout that was introduced with Core 6.2. And overall, the data delivery is based on a best effort mechanism, but faster because of the shorter connection intervals. So to wrap up, the ULL HID project enables report rates of 1 kilohertz or better to target HID latencies of 1 millisecond or less. ULL HID closes the latency gap between Bluetooth and wired HID. ULL HID delivers capabilities and performance to meet the responsiveness needs for next generation HID designs. The ULL HID project brings to developers two methods to achieve ultra-low latency, HID ISO and HID SCI. And in terms of an adoption timeline, HID ISO is already out the door. HID SCI is coming out in late Q2 with HOGP version 1.2 release. Finally, at CES in January, we had the opportunity to showcase a demo for ULL HID based on TV-based cloud gaming with ultra-low latency on a gaming control. The implementation was based on LG OLED TV and Bluetooth gamepad from a manufacturer called Razer, which you might know. So ULL HID, it's already in the market. It's out there. And we hope that this is going to start picking up faster with the introduction of HID SCI very soon. That's all. Thank you for your time and attention.